last we left, we had seen how introducing pipelining created problems. We called these problems hazards. And the problems were fundamental to how the pipeline was constructed. So if we considered these two instructions, add and add, we discovered that we couldn't execute the instruction in red when we wanted to because the value that it was going to read from RBX wasn't there. And we inserted no ops so that we could deal with that. But clearly there's got to be a better way. So let's go back to what the fundamental problem here is. In order to execute that red add instruction, we need to have the right value in val A that the previous instruction is writing into RBX. However, that value is stuck in the middle of the black instruction's execute phase, right? It's nowhere near being read into the register file, which is what we need in order to get the right value in val A. So do you think maybe there's a way that the hardware could help us? The answer is yes. There are a couple of different ways. The simplest way is for the hardware to just say, well, instead of making you insert no ops, I kind of like know what the problem is, so I can just halt the processor, not completely, but I'm going to do what's called stalling it until the data gets to the right place. And you may not know this, but your handy dandy y86 simulator actually gives you the ability to run a pipeline that does this stalling. So let me pull that up. So here's essentially our add program with these two dependent instructions. Now you'll notice that I've loaded those registers with some values so we can see it, and I've gone ahead and I've explicitly inserted some no ops so that the values will be in the right place when we start to execute. So we always reset first. Now let's run. We'll run our 3 IRQ instructions, IRMoveQ, and then we're going to do these 3 no ops and set ourselves up to start executing the first add instruction. So you look and you see that the right values are in registers RAX, RBX, and RCX. And now the first add queue is in the fetch stage. And that's fine. We'll run one more cycle. And now the second instruction is in the fetch stage, and that first instruction is in the decode stage. Now before, when we used the naive implementation, the pipeline would keep moving and the wrong values would end up in the wrong places. I'm now running a pipeline implementation that does stalling, and we're going to watch and see what happens. So the first instruction is going to move into the execute phase. That should happen just fine. The second instruction should move into the decode phase, but during that decode phase, it normally reads the register file. So what happens? The processor says, I need to stall that add queue. So it's sitting there in that decode phase, but I don't want it to go anymore. The first add queue is going ahead and executing in the execute stage. The first one is stalled and the one behind it is stalled because as long as this add queue can't move, the one behind it can't do anything either. So now what happens when I run one more cycle? What you see in the simulator is that we insert what's called a bubble. And what the bubble means is we want that first add queue to proceed to the next phase to get to memory. But this add queue, we don't want to go anywhere. It's got to stay in decode. Well, then the question is, what ends up in the execute phase? And the answer is nothing. So when we stall an instruction, the pipeline is going to continue to move ahead to let the instruction that's causing the problem finish, but we need something to kind of fill the pipeline, and we call these things, which are essentially no ops, bubbles. So rather than you, the programmer, inserting no ops, the processor is inserting these bubbles. So just like you inserted 3 no ops, the processor inserts a second bubble and a third bubble. And only after it inserts that third bubble is that add operation allowed to proceed. The same way, when you added the third no op, that allowed the processor to get the right answer. So let's go back to the slides for a moment. Okay, so here's where we left off. So stalling is this idea that the processor, rather than asking the programmer to insert no ops, will just stop the pipeline. So let's look at what's really going on there. Here's our normal diagram, and we have these two add instructions at positions A and B. Now, when will instruction A's new value get written into RBX? Well, values get written into the register file during the write back stage. So if I'm writing it during the write back stage, the next instructions don't have access to it until the following time cycle. So if we need that instruction in the decode phase, right? So if we need it here, then what's really happening is that the stall is kind of wasting those cycles that happen during B, C, and D, because this red add instruction can't continue running until its decode comes after the write back. So I encourage you to look through that carefully and think about it. Now, until now, when we talked about the performance of processors, we'd really talked about the processor itself, right? How long does it take the processor to do things? Now that we've introduced stalling, we can actually start to talk about the performance of a program running on a processor, right? So the latency and throughput are really just calculations about the hardware. But in general, we don't care so much about just the hardware. We really care about how well a particular program runs on that. And so we introduced this new metric called CPI for cycles per instruction that says when we run a particular program, how many cycles does it take for each instruction? Right? Now, what's the best we could do on the y86 processor? Well, the best thing we could do is that we could execute one instruction every single cycle. And a CPI of 1 is considered sort of the gold standard. But in modern processors, they're what's called superscalar, and they can actually execute multiple instructions simultaneously, not just in this pipeline fashion. And so it's possible for modern processors to actually get a CPI that's less than 1. But for this course, our goal on y86 is really to see how close we can get to a CPI of 1. Let's go back to the simulator for a moment so that we can look at how we might compute CPI using the simulator. Okay, so here we are. And in a perfect world, and what I'm going to do is I'm actually going to add a halt instruction here. So in a perfect world, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 instructions, and it would take us only 9 cycles to execute it. So let's see what the processor tells us. Rather than going through one at a time, I'm just going to click Start. And it says it retired 9 instructions. That means it fully executed 9 instructions. But it said the clock count, it took 16 cycles to do that. Now, you should be getting a little suspicious here because we had 9 instructions. We saw that we inserted 3 bubbles. So that should be 12. Where are the other 4 instructions coming from? Well, remember, the halt, that last instruction, has to trickle through the pipeline. So when our program ends, we're always going to get these 4 extra cycles added just to make the program take that last instruction and run to completion. When you're computing CPI, you often ignore those ending instructions. And so we'll really focus on the body of a program. But I wanted you to see what happens in the simulator, that it really does count how many cycles it takes for the whole program to finish. So if we do this one cycle at a time, what you see, and I'm going to zip through it pretty quickly. Okay, so we do the add queue. Now we get these 3 bubbles added. 1, 2, 3. And now the halt comes into the pipeline, but the program actually keeps running until the halt gets all the way through all the stages of the pipeline. You're going to get lots of practice counting bubbles, figuring out where they go, and playing with the simulator.